One thing as the chat actually, it only works for the people who are online when
Yep.
you, yeah, okay.
I know. I can repaste it.
Okay,
or you
great.
can share it with the minutes if you write the minutes, so you can put it in there.
Yeah.
There is more detailed information about those balancing markets in Finland.
Okay, great.
Does that show up correctly? Yes. Just a minute. All right, we'll go ahead and get started. I'd like to welcome everybody to day 2 of the CSC Lumi Technical Showcase. Just a few logistics for everybody. Oops, if I click on the right thing. The workshop event website is here. So if you want to pick up slides and any other content, it'll be located there. It includes the agenda, abstracts, and bios. And yeah, we're uploading presentation material from yesterday and then today as well. So also a reminder that the working group website is eehpcwg at llnl.gov. Just a reminder on etiquette, please mute your microphones and turn off webcams. Use the chat for Q&A. And without much further ado, this is the agenda for today. We'll jump into the Lumi use cases, heat reuse, installation acceptance, and then some lessons learned. So quite a full agenda. So first up, we'll have use cases in current and future. So I'll stop sharing and let you take over, Pekka.
Thank you. Good morning, good evening. I wanted to present a kind of like a reminder for us all in the HPC why we actually do this what we do. So of course we do it for science and scientists and research and innovation in general. So I uploaded or sent Natalie a thick set of things that we've been collecting now after the early months of or the first year of Lumi operations. but I won't go all of them through. So they are a bit busy in terms of text, and there's a much more on the deck that I sent. But I'll just like going to tell you a few, or like just like highlight a few of them in no particular reason, just like cases that I'm personally most aware of. Perhaps was the basis for the selection. But yesterday we reviewed the Lumi's design criteria, and we wanted to be able to host very complex workflows where we can combine traditional simulations, well, you know, like a AI training AI networks out of those results, analyzing or this kind of data assimilation of observation data and computing some of the top of that. And in fact, we have quite good showcases where we can get to when with this kind of workload what we can achieve. So the digital twin is of course a buzzword, but here we have a very cutting-edge science that build this kind of very complex models that they refer to as digital twins. So well, our kind of like a crown jewel on this very complex workflows is the Destination Earth. It is an European Union funded very big this kind of moonshot initiative where they want to build a digital twin of the Earth in terms of its climate, and the kind of climate and basically everything to affects it and affected by it. And the idea is that this would be so powerful, so accurate piece of software that one can base political decisions on top of it. And so it's been contracted by the European Center for Medium Range Weather Forecasts, the European Space Agency, and the European Office for Meteorology Satellites, EUMETSAT. And so one of these is known as the climate change adaptation digital twin. So this is something that we've been now for it's 1 year old project. We've been implementing it on Lumi with an idea that there's an Earth system models, so ICON, IFS, and then ocean models that basically produce certain way of the climate very long. So the decadal, so 50, 60 years of long simulations, but with so high like a spatial resolution that the error bars are like a small and that this very reaches to the local scale. So I think it is one of the most like ambitious high performance computing project I ever seen, but with the also stakes high that this software suite once completed is something we can really use to understand the impact of climate change and also help in preparation, in mitigation, understand this kind of what if scenarios. If we do X, how does it impact the climate of the 2040s? So this is a one very nice example. And for instance, if looking at the global climate models on Lumi, so if you think that the IPCC reports are typically, or the typical climate simulation is done on over 100 kilometer spatial resolution. So we already can show that on Lumi we can basically routinely do 10 kilometer global resolution. So every grid point distance on a normal state of the art is already like a 10 times 10 more grid points covered, and having this kind of like a not yet like a storm resolving, but something towards that line. And also we have demonstrated we can like run almost one simulated year per day on Lumi on this kind of a resolution that already is able to capture storms or even individual clouds. And this is the whole globe. So this is a much higher than the Finnish weather forecasts are done, but it's a globe and it's a multi-decadal run. And basically it's showing that we can approach the 1 kilometer spatial resolution on climate change, climate simulation. So the destination Earth will be in this point of time. The production simulations will be done with the 5 kilometer resolution. So the other part of the destination Earth is this extreme weather digital twin, basically that takes from the global to the local scale. And really help to understanding and forecasting in advance this kind of extreme weather phenomena like floods and similar and landfalls and so on. So these two will the first two twins of the Destiny thing, and then the EuroSPC machines, including Lumi, are kind of like a well positioned here. And of course we discussed on being climate neutral system, but also we want minimizing the carbon footprint, but at the same time we want to kind of like maximize our fingerprint or handprint in what comes to the understanding and combating climate change. Also to the same line, little on the same perimeter is this biodiversity digital twin. So basically building very complex ecological systems, so understanding how the living quantities qualities and then how do like a different distributions of species behave, and with an idea that one could take the climate trajectories as an input for also for the predicting how biodiversity and different habitats are developing. Then so starting from the digital twins, then one thing that keeps the system very busy is obviously a very big buzzword of generative AI and large language models. So it's I think close to 1/2 of the cycles probably will go at the moment on training very well this kind of big large language models that are basis for everybody knows GPT, but this time this kind of like a with an idea that these are by researchers funded with public money, so they are these models are open source, so the data is training data is open, the network the outcomes is open, anybody can take it for their further use and also understand it. So it's like a transparent and kind of a democratized access to the generative AI. So we have one on the European languages, high performance language technologies project, and then for making a state-of-the-art English model by the Allen Institute, which is in fact a US-based institute, but we are collaborating with CSC and AI and the Allen Institute and AMD for generating this Olmo. And the first results of the Olmo model start to be ready. So this people made it's public, but we haven't made any press releases out of it yet. But on the Allen Institute, on the blog posts they have been also describing the progress towards the Olmo. But at the moment the kind of like a quality of this start to be on the nearing the what OpenAI has for the ChatGPT models. So it is really a state of the art, but it's open source to the last bit. So and like I said, so it is this kind of a the openness is really the thing here that we have a open access to this technology too. So and then the next items come from the biohealth side. So they have been very impressive work towards this kind of digital pathology. So just pattern recognition to like replace human pathologists. There have been traditional molecular dynamics for different understanding the cause of diseases. And in this case, the Alzheimer's disease. And then many others, such as like a took two story, but they are more on the set that I shared. On the material science, this cases really show nicely the idea that material science is not just anymore about single point calculations that you just they become so routine that we are in a situation where we really can produce a lot of different single energy calculations and then make like analytics on top of that kind of on the fly. So for instance, there's DFT density function theory calculations, but like a training neural networks on the fly with the results to be able to really make prediction of this very complex potential landscapes based on different material science questions. And similarly, there's also from this case of same approach, but building this kind of a database of quantum mechanical calculations, and then building the machine learning model for it, and then using it for designing new materials. Also, physics has been always the driver case for high performance computing, and hasn't gone anywhere. So obviously there are many this kind of like a fundamental physics question being solved on the system every day. So something around the structure of a proton, this kind of like a this is like a quantum superfluid, but not on bosons, but with fermionic states, meaning that you have to build the full state vector of this matter. So very exotic state of matter, but possible to do with Lumi-sized machines. So this was the largest direct eigenvalue equation solved until now in basically in history for solving this very one big state vector of this system. Also, heliophysics, solar physics have seen some magnetohydrodynamics codes seem to be screaming on this kind of architecture. So there have been already very nice results out of it. So one, well, this was mostly like a Lumi C one, but especially this one where this by Aalto University and Max Planck Institute, where they find this kind of like a long time ago predicted mechanism under the surface of the sun. If you can think of this, there's a numerical verification or numerical proof, but this really sort of like a find from this kind of first principle calculations, find the existence of this mechanism, and it will help in predicting like a solar flares and magnetic storms on Earth. So this was a really nice breakthrough, and I think one of the highlights so far on Lumi. On the CFD side, Lumi was a Nobel Prize finalist from the NECO CFD code. He didn't get selected, but also just getting there was a really nice exercise, and they basically scaled the code to the 80% of the Lumi with the perfect scaling. And also on the CFD side, this kind of like a computational glaciology was a very big very big glacier models have been able to do while going to the big GPU systems. So this is just a fast walkthrough of this cases. So the like we discussed yesterday. So with this we have a really big user base. So whole of Europe and hundreds of projects, 2,000 user accounts, and with an idea that we want to bring some value add for pretty much all relevant excellent science of this decade. But yeah, no, not to leave room for the technical discussions upcoming. I pause here and take questions if Aaron wants to have them now.
Yeah, are there any questions? All right. If there are questions, there'll be some time at the end for Q&A as well. So let me reshare. So next up, we'll have Asa, and he'll be talking about heat reuse within the facility in more detail.
Okay, good evening on my behalf also. I will share my screen, so just a second. Is it visible?
Yeah, it looks good.
Okay. So good evening, my name is Heiskanen. I'm today here to discuss and tell you about the Lumi data center heat reuse and district heating that we are doing on the Lumi. So just quick recap from yesterday's, if there's a people online who wasn't participate yesterday. So Lumi is installed in this old paper mill area, which was announced that shut down the paper production in 2008. And it was obvious choice to utilize the waste heat from the Lumi because there's a district heating power plant located in the area, just couple of 100 meters from our data center. So it was very cost effective to utilize the waste heat usage from the Lumi. So couple of things about sustainability and metrics depend about the heat reuse and other topics. So waste heat is reused about for district heating about 9 months in a year. It's dependent on the district heating network demand because this power plant in this area has its minimum operational power. And we are also providing district heating for this business park area. It is also using district heating to heat up the buildings in this area. So basically, when this power plant is reaching its minimum operational power, the heat reuse from the Lumi needs to be limited. And this usually only applies during the daytime in the start and in the end of the summer when the daytime temperatures increase and demand on the district heating gets lower. But also in the summertime, this district heating power plant has usually the annual maintenance break, so we are able to utilize the district heating from the Lumi 4 to 5 weeks in the hottest time in the summer. Individual heat pump COP value is up to 4.7 with 100% load, which is stable and optimized. So all water flows and temperatures are optimized for the heat production. But overall COP, what we have been seeing so far has been around 4 in the HPC operations from the Lumi. We haven't implemented any evaporative water cooling in the dry coolers because of our cold climate. So average temperature in Kajaani was in 2022 3.6 Celsius, and highest measured temperature so far in this year, well, in this year has been 26.2 Celsius. And while we decided to build this our data center in this old paper machine building, we assume that we have reduced CO2 footprint of Lumi data center construction by over 80% while comparing this brownfield solution against construction in all new building for the Lumi, and approximately it's 1,000 tons of CO2 emissions. JP had a presentation yesterday where these calculations was in more detail visible, so you can check those calculations on those slides. So here's a graph about the average temperatures in Kajaani in 2022 and 23. So as you can see, our climate is pretty cold and average temps are pretty low, because in the night time, even in the daytime, if there's 7 degrees, it gets pretty much lower in the daytime. So district heating demand is quite a good in a yearly level. Then some specifications about our heat pumps. So these heat pumps are manufactured by Mitsubishi Electric Hydronics and IT Cooling Systems SPA, and those are made in Italy. This refrigerant gas that is used is R123GE, which is a multifunctional gas with low global warming potential and ozone depletion potential. And it is displacing and has displaced this previous R134A gas, because this has much more lower environmental impact and good thermodynamic performance. Fluid that we are running in the heat pump, so we are running water and evaporator and condenser side, so there is no any other chemicals involved. Each heat pump has a 4-pitcher screw compressor, and they have cooling power of 2.4 megawatt on each heat pump, which makes total 7.2 megawatts of cooling power, and heating power 3 megawatts of heat pump, and total 9 megawatt of potential district heating and waste heat utilization. Single heat pump is operational approximately from 20% load onwards, so reasonable operation power for the heat pump this size is 600 kilowatt of cooling, and it makes us 750 kilowatts of heating on that load. Then some statistics about the heat pumps, and maybe I said yesterday that these are running the different operational voltage than the usual 3-phase devices in the Europe. So IT devices has this 400 volt, and these nominal voltages 690, and power factor is pretty good on this kind of device. And as you can see from the power input with the 50% load, power input is pretty much higher than in the 100% load compared of the cooling capacity and heating capacity. So this makes these heat pumps COP value much worse when we are operating in the 50% load instead of 100% load. So this COP is approximately it's worse in the partial loads below the 50 to 60%, but after that COP value is in the pretty good level, and this has huge impact in the heat production profitability. So you should be able to operate highest load as possible with these heat pumps. So then about district heating specifications. District heating power plant, which we are providing this district heating, which is providing district heating for the city of Kajaani. we have two 4 megawatt heat exchangers, so we can provide in total of 8 megawatt district heating for the city of Kajaani. And this is controlled based on the Lumi's IT load and district heating network demand. And then we are also providing district heating for this business park area. And there is currently one 2.5 megawatt heat exchanger installed. And this is controlled based on the return temperature of the area district heating network. So if it gets too high, we know that there is not enough demand, and we start to restrict the flow to the area district heating. So we are running 80 degrees outlet from the heat pumps, and it's returning approximately in the 58 degrees Celsius back to the heat pumps. And this connection pipe between our data center and the customer's heat exchangers approximately this 200 meters. So those are pretty close to utilize the waste heat from the Lumi. And these cooling pipes are done.
Me acabo de pujar al meeting de que
and this cooling pipe material is carbon alloy steel. We have two ways to provide district heating for the city of Kajaani. So there's return and supply connection to the district heating. So basically we are running this 80 degrees Celsius liquid from our heat pumps to these two heat exchangers. And we are in this connection type, we are supplying it directly to the district heating network, which goes in the city of Kajaani. And we are taking a partial water flow from city returning district heating network and preheating it, heating it again. So this is the connection that we actually use when there's a maintenance break on the district heating power plant, and it depends what is their desire. So actually most of the time this year, I think that we have been done this return supply connection this year most of the time. So then we have this return connection to the district heating. So in this we have a side flow from the returning water flow from the Kajaani city, and we are preheating this return to the district heating power plant. And on this connection, this district heating power plant can adjust the production based on how much waste heat we are providing from the Lumi. So we are preheating the returning district heating from the city. So these are the two connection types that how we can provide the district heating to the city of Kajaani. Then about the cooling itself, these are the same slides that I had yesterday, but I will go through these quickly. So this mechanical cooling, we are actually utilizing all the waste heat from the Lumi. So depending on the Lumi IT load, we are able to operate up to the 9 megawatt of district heating with these 3 heat pumps. So all the cooling is done with the heat pumps. So mechanical cooling is utilizing this 32 Celsius outlet through the buffer tanks back to the Lumi. And return temp is somewhere 42 to 44 degrees. It depends a little bit how much load there is in the Lumi. Then we have this partial free cooling with heat pumps and free cooling heat exchangers and dry coolers in the rooftop. So this partial free cooling is used every time 15 minutes in the cooling group module. So this one cooling group module consists of heat pump and heat exchanger and dry coolers. So every time we start the cooling group, we are using this partial free cooling 15 minutes. Or if there is an alarm on the heat pump, active alarm on the heat pump, or the heat pump outlet exceed this 1.5 Celsius over the set point on an individual cooling group. So one of the cooling group can be fully mechanical cooling, and two of them partial free cooling or vice versa. So these are individually operated. Then we have this partial free cooling with power limit, and this power limit is used if the district heating power plant indicates that there is not enough demand on the district heating network. So then we bypass part of the heat load from the Lumi to the free cooling heat exchangers, so we can adjust the heat production based on the demand that there is on the district heating. And this usually only applies situations that the daytime demand is lower than the nighttime, and we are still pretty much just started the district heating production season, or it's closing to the end. Then I have some graph about the delays on the district heating. So this red line indicates the point when we have started third cooling group module. So in the beginning, this is actually from this fall when we did Lumi benchmarks. So we had an idle load about 3 megawatts in Lumi C and Lumi CPU and GPU partitions. And when this HPR run started, electrical power increased very fast, and we are starting this cooling group modules based on the electrical power, not when it's radiated the water. So third cooling group module was started immediately when the electrical power increased. It takes a couple of minutes that it starts to radiate from the Lumi secondary cooling loop to our primary cooling loop, and it takes little time when it hits the heat pumps. So we have quite a big volume in our cooling loop, so it takes a couple of minutes, up to 4 minutes before it hits the heat pump. And as you can see from this line, that heat pump starts ramping up the power pretty slowly, so it takes over 10 minutes that they are reaching the operational power. But when the power is reached, the production is pretty stable. And in the end of this run, the district heating radiated heat to the water start decrease slowly, and the district heating follows up. So this is maybe the worst case scenario on operational of the district heating when the heat load swings are this high, but in the normal operations, this usually don't happen, except when we have a hero runs, when we allocate full GPU partition for the single user, which we are done in once in a month if there is a request for those. So then I have an example from this November about the district heating. So this column below is district heating the city of Kajaani, which is obvious bigger. There's a bigger capacity, and this is district heating to the area in the top of the column. So we had a maintenance break in the Lumi. We had this last integration break before the final. So now that Lumi has been finally installed, so we had this last maintenance break, which ended in the beginning of the November, and we were able to start our heat production again here in 8th of the November. This is Lumi's direct liquid cooled cabinets power. So this includes only the liquid cooled partitions of the IT load, and this is the total consumption. Total site power consumption. And this yellow line is energy reuse factor. So how many % we are able to utilize energy that we are using, we are able to utilize for the waste heat. And as you can see, when we got our heating production pretty stable, we are able to provide more than 80% of used energy. We are able to reuse the more than 80% of used energy back to district heating. And this is something that we are still optimizing. So heat production is still, we are doing the fine tuning on the system to find out the perfect parameters to run the district heating on the Lumi. Also in the Finland we have some drivers to implement heat reuse. So actually in the Finnish energy taxation there was made a change in the beginning of 2022 that data centers that are fulfilling these energy efficiency requirements are able to apply for this lower energy taxation class, which is much cheaper in operational costs than running the data center with the class 1. This used to have a limit that only data center that average IT power per year was over the 5 megawatt. So those was able to apply this lower energy taxation before the 22, before this change was made. But now even the smaller data centers that are exceeding 0.5 megawatt of IT load, they and are fulfilling these energy efficiency requirements are able to apply this energy taxation class 2. If data center cannot, from technical or economical reasons, utilize the waste heat, the PUE requirement needs to be met. So in our case, when we are utilizing the waste heat and our annual IT power so far in this year is maybe between in this range, our IT power calendar year average needs to be below 0.9. And if data center is running IT power between 5 to 10 megawatt in average in a year, the ERE value must be below 1. And data centers over 10 megawatt, this ERE requirement does not apply, but PUE requirements need to be met. And for the PUE, it's currently PUE needs to be below 1.25, and from 2026 it will get more strict, so that PUE needs to be below 1.2. So there is a huge benefit for the operational cost if waste heat is utilized, or the data center can fulfill this environmental and energy efficiency requirements. So about heat reuse in the future in the Kajaani. So this our local energy company that is operating this district heating power plant, they announced in last July that they are investing in a new carbon neutral heat production in the Kajaani. And their goal is to have a carbon neutral heat production in Kajaani by 2030. They will replace the existing boiler. It will be converted to be operated by the pellets, which are usually produced from wood industry side products like sawdust. And currently it's running with the oil. They are going to install a new electrical boiler and heat pumps on the site. So benefits for the data center would be that they don't need to operate or invest on their own heat pumps if the waste heat can be utilized directly from the data center to energy company with heat pumps that they are operating. And my opinion is that waste heat transfer to the heat pumps is more energy efficient than using the dry coolers to evaporate heat outside. But this is something that maybe could make some calculations in our current installation, that how much energy we are using to only transfer this heat load to the district heating instead of when we are running it on the free cooling. So this would be something that could be investigated a bit further. But this will end up with the low PUE, low ERE, and high ERF value. Then about these metrics, which we have, PUE is traditionally used to define the energy efficiency of the data center, but PUE is not a good measurement if the data center operates heat pumps by themselves for the utilizing waste heat. It would be huge difference if the waste heat can be utilized as it is without priming it in the higher temperatures with the data center operated heat pumps. So better measurements for this kind of data centers that VR is ERE value, which is total energy minus energy reuse divided by the IT energy, and this is quite a much easiest value to compare with the PUE. And this energy reuse factor that I have on this graph indicates how much energy is reused in percent compared to the total energy that has been used in the data center. And this COP coefficient of performance indicates how energy efficient this heat production is. So this will indicate how well the heat pumps can utilize the waste heat and how much power they will use to produce the district heating. So some values from the Lumi data center so far this year. So these numbers has been updated in the end of November. Our free cooling PUE is below 1.05 if we operate free cooling. PUE with the heat reuse is somewhere a little bit over 1.3, and this is something that we are aiming to get lower, below 1.3 in the future. Heat reuse COP has been somewhere like about 4, and this is also that we are still doing the optimization and try to get it better, because in the individual heat pump it can be up to the 4.7, and those pumps that are transferring this heat are not consuming that much energy compared of the heat pumps. Annual ERE, so this is calculated for the full year, is 0.534, and on those months that we are not providing the district heating, the PUE and ERE equals, so those months will increase the ERE value. And energy reuse factor is so far this year 0.6, so 60% of used energy we have been able to utilize for the waste heat. Our annual heat production so far is a little bit over 22 gigawatt hours, and this, based on this amount of heat production, approximately we have reduced CO2 emissions over 3,500 CO2 tons. And this CO2 emissions is based on the district heating production plant average CO2 emissions from last year, which was 161 kilograms per megawatt hour. So we don't have real-time data available or statistics yet from this year, but we will update the numbers when we have 2023 data available. And our data centers are running 100% in the hydropower, so basically operating these in the energy consumption of the data center is a carbon neutral in the operations. So thank you. That was end of my slides. I will stop share. I can see that we have some questions in the chat.
Yeah, there were a number of questions. One of kind of start at the beginning is Natalie originally asked how the heat provided by your district heating system was handled before by the supplier.
Yeah, so the district heating was produced in this district heating power plant, burning the fossil fuels, and there is some, so they are basically burning every type of materials like waste and fossil fuels. So carbon emissions from that power plant has been reduced while we are now providing the district heating. And this area was also using the district heating, but that was supplied on that power plant. Yeah, Pekka has answered that they are burning pretty much everything that burns.
Yeah, there's I encourage everybody to kind of follow the chat on the details. I had a question too, as far as you said, the Lumi is able to provide 80% of the district heating demand in most cases. Is that correct?
80% of total of Kajaani district heating. No, the actual number that we did use on the beginning of the before we implemented and started to reuse the waste heat, we make a assume and calculation that it will be something like 20% of the total of Kajaani district heating demand yearly.
Okay.
And next year is maybe the first full year in the operational when we can see how much we are able to produce the district heating yearly, because now Lumi is fully installed and we have been able to operate our heat pumps now in the good power so far in this last fall and big couple of last months in the current winter.
So create a little, or any other questions from those online?
How is excess waste that is no longer being burned being dealt with? I think that JP had those district heating emission factors from 2022, and distribution was peat 41%, wood fuels 56%, and natural LNG 2%. So they have been able to reduce usage of those while we are able to provide district heating for the area.
But I think the question, so actually I don't know, but I know that there is a lot of other companies who are generating the district heating in Finland. So maybe some others are now buying that, but and like Pekka mentioned, so peat is not anymore harvested, or at least so much harvested in Finland like it used to in the previous years.
Yeah.
So I thought the tax implications were quite interesting, and kind of the levels of 10 megawatts with different requirements. Just curious if there's any thoughts on future adjustments to that kind of tax environment, or if there's much movement on that.
Sorry, what was the question?
Yeah,
about
maybe.
this?
So I thought the various levels of where your PUE or ERE requirements were set in that, I assume, legislation on tax requirements.
Yep.
If there's any ongoing discussions about refining those or changing those in some way.
Those has changed recently, so I don't think so that there is no need for the changing those days. The recent ones are kind of in use in 1 year or maximum 2 years. So those are pretty new ones. So I think if you so once again those figures, but I think the PUE value we are not yet achieving the limit that we get the relaxation for taxes. But this energy reuse factor.
Yeah, just a second. I will scroll.
So
Yeah,
that,
it's
okay,
0.
there is a mention those, yes.
Yeah, and if the data center cannot utilize the waste heat, they need to meet this PUE requirement. But if the waste heat is reused in some form, you need to meet these ERE values.
Yes.
And these are pretty easily achievable with our kind of heat reuse implementation.
Yeah, because in our case, this heat pumps energy is calculated to the PUE figures. So, like as I mentioned,
Yeah.
without those heat pumps, we are 1.00 level. But
Yeah,
because
yeah,
we are using those, yes,
yeah, we could end up these low PUE values if we don't operate the heat pumps by ourselves or even below.
All right. Why don't we keep it moving?
Thanks.
All right. So next up, we have a bit about installation acceptance.
Hello. Just a moment, I will share my presentation. Can you see it?
Yeah, looks good.
Is the audio okay?
Yeah, audio's good as well.
Okay. So Lumi installation and deployment project. So first of all, about myself, my name is Samuli Saarinen. I'm a development manager, leading the computing platforms group at CSC. So it's a sysadmin group responsible for actual production and administration of our systems. I have a background at industry, so basically supporting research and development and HPC at telco from early 2000. I've been at CSC from 2007, and basically like last 10 years, I have mostly spent on large scale top 100 HPC system deployments. Our national systems, Taito, Sisu, Puhti, Mahti, and now your HPC Lumi, I've been a project manager for installation and deployment. I've also worked in European projects. I noticed that there are many colleagues who know me from Grace. So I think like first things first, I think this is a nice opportunity to also like thank everyone involved with the Lumi project. So we had a project kickoff in November 2020. And really the involved persons and groups from CSC, we have our group, we have the data center facilities, we have the networks group, we have the Lumi program office, Lumi user support team, HPC support, computing environments, communications, and many more. And of course, we have the EuroHPC JU supporting us and steering us, and Lumi Consortium. And of course, from HP, management involvement, project management, account management, service management, and technical experts. So it's been a long project. So first phase was accepted in October 21, second phase in January 23, and additional third phase October 23. And there have been like at least like 200 persons, named persons I know, who have been directly involved to make this happen. So a big thank you for this. And little bit continuing about the people were in this kind of like project. The meetings. So from the first day, we have had these like weekly all hands meetings. This is a must. You cannot really skip the weekly meeting. Having like all persons from the supplier and hosting entity. But also because we have this segregation of duties, for example, that one group is responsible for network, one is for the data center, and we had like many parallel projects at the time. We needed also internal coordination meetings. And then of course steering. So we had internal steering groups and external steering groups with JU and HPE. And because this was a phased installation, and we already went to production with the first phase, then we started actual service meetings. And about like 1 year from project start, we also started like daily Scrum meetings. And of course, all the time, the fact was that for example, my team, when they were not in these meetings, they were actually in this shadow meeting all the time with HPE. So it's a lot of work. So overview of installations. So the first phase was the CPU partition, 1500 nodes, and all the storage devices and some like special nodes. And on Q1 of 21, our data center was ready and waiting, like white space, completely waiting for the system. But then we found out that first of all, we are still in the middle of pandemic, and there was the component supply chain shock. So the system was delayed. And also travel arrangements, they were like really difficult. And for this system, the site inspection, which is extremely important, it was done like completely virtually with our data center facility specialist presenting the whole data center online with cameras. I think this is like really unheard, unexceptional for any tier 0 system or even tier 1 system, but it really worked well. On the other hand, the classic technology, like having traditional paper cut silhouettes for floor cuts, that's like highly recommendable. So you actually know that exactly where you're going to place the system. So there were some delays, manufacturing, but also software. So at the time when we were waiting for the system, kind of like a first version of the system software, Shasta 1.4, was late. And that was basically, I think, the first usable production okay version of the software. So we couldn't even like start training our sysadmins. The system was built and installed at the factory. And it actually waited at the factory for this first release of system software that is good enough for production. And then it shipped end of June 21. System was accepted in October, but then we already had some like bad news about the second phase. So it was also going to slip right. But meanwhile, we still started operations with the first phase, and also supplier HP started building the local support team and services to Kajaani. So the second phase, that was late, and the expected date was Q2 22. And this meant that it's a second summer, basically main installation in July or something. And this phase 2 shipment was split to sub-shipments. And these first 2 cabinets, they were set to independent system. It was running with a new Slingshot 11, 200 gigabit interconnect. It was like a completely working supercomputer. We actually used our test and development system as a management layer for this temporary system. And we got that benchmarked and went to number 3 on top 500 June 22 with over 150 petaflops of sustainable performance. Then in early summer, rest of the cabinets arrived on site, but there was this really challenging integration problem. The Lumi C was still deployed with the old network, and all the GPUs were with the new network. So we actually had to change all the NICs in CPU partition to these new Cassini adapters. And meanwhile, we also needed 2 major updates. I think they were like codenamed Strawberry and Raspberry to get these systems actually like operating together. And this maintenance was very long. It took up to 7 weeks. Eventually, like after the acceptance procedure, the full system was listed on November list with 309 petaflops. And it also survived our 28-day availability test and was finally accepted in January 2023. Then we had also this additional phase 3 that was partly because there was, of course, this requirement of reaching 375 petaflops. And one of the problems was that the TDP of GPUs was originally 500 watts, but it was increased to 560. And because of the European power standards, and I think Esa and JP can explain this better, we get less power in a rack. So the original plan was that the cabinets were depopulated, and now we started actually repopulating the cabinets. Also, we added 1 extra cabinet. And for power and cooling, this was easy, but adding like 1 extra cabinet to large system the network configuration, it's a major work because there's all-to-all cabling. In a final configuration, Lumi, there's about like 64 kilometers of slingshot interconnect cabling. Also, the final benchmark this fall was very challenging because there was like a small variation of performance of GPUs or nodes. And at the same time, we have this power cap. So finally, we did an analysis and actually used this power capping for selecting a slightly lower GPUs and just boosting those to get like a optimal power curve or performance curve. And then finally, Lumi now in November listed number 5 and 379 petaflops. Little bit about the system acceptance procedure. So this is kind of like an ideal perfect world. When the system is handed over to us, we have this physical inspection, 1 to 2 days. We check the overall quality. We check cabling, labels. We check that there's no visible defects, no blinking red LEDs, no physical contamination like dust or particles or any leaking pipes. Also, we go through the handover documentation, and then we have complete shutdown of the system, and we restart the system, and then it's basically like a clean start, and we can start our functionality testing. And functional testing, that's like 1 to 2 weeks. We can basically test anything that's a mandatory requirement, or we can test anything that supplier has promised in their response to a tender. System management stack, any capabilities, functionalities, even compilers, monitoring system. Also, during the functionality testing, we already want to test the power consumption, and that's done with the HPL because that's expected to be a peak power. Then there's like 1 week for benchmarks. So we are just like verifying the results. And then there's the availability testing, 4 weeks or month, real pilot use cases, real workload. And then we are finished. System can be in general availability. So this is the perfect world. Actually, the reality check, during the physical inspection, there will be these red blinking LEDs. Also, like checking thousands of cables, it's not realistic. So basically, checks, they are based on samples. You cannot like open every single blade and check that if there's dust. But the problem is that if there's anything wrong, for example, with the network, we will find it later. Sometimes you can find some miscabling years later and find out that okay, that was the reason for this problem. Then the second thing is this system restart. It sounds like reasonable and a minor thing, but in fact, it's a leap of faith. These modern top-tier systems, the installation and complexity of the software stack and all the modifications, are they actually in actual configuration? So even on a day when supplier knows that, okay, it works now, you cannot really be sure that does it work after the reboot. Then the functionality testing, 1 to 2 weeks, test everything. But for example, for Lumi, there was over 50 functionality requirements that has to be tested and also logged to have evidence that that test is completed. Some of the tests are like really trivial, but some of the tests, they are not. And of course, like one first problem is that running HPL, that's a hard task. That's very often the showstopper for accepting the system. I think it's still like a best demonstration for system integrity because it's so difficult. But doing this in a first stage, I think it's too difficult. And with these large systems, with any kind of like mean time to failure, HPL challenge, it's getting harder to reach. And the time, person work, energy we use for this, is it really worthwhile? Should there be some kind of like other method, easy like burn-in test to just test that the electricity maximum envelope don't go beyond the site limits? Maybe an aggregate test, maybe some kind of like combination of mixed precision, HPCG. But I think typically I like this running the HPL, it's the hippo or elephant in the living room. Then there's the redundancy test. So if there's anything which is redundant, you should actually test it during the functionality testing. Rack by rack or power supply by power supply. To make sure that, for example, that if you lose one power feed, the high availability parts will still stay up. But there is this problem that it's when the system is not accepted yet, it's supplier property. So this high risk testing causing like blackouts or maybe like removing complete disk shelves from the storage. If something like breaks badly, whose responsibility it is? So I think this is something that typically you really have to discuss with the supplier and make a plan. Then the benchmarks. So of course, idea is that you get a benchmark report, you just verify the results, but it's not like that. Very often, actually, like after the functionality testing is the very first time that some codes are run in that actual scale. This is especially true for landmark installations. And if you have any shortcuts with previous stages, it will backfire here. Then the availability testing. So we have typically 4 weeks, 24/7, real users, real codes, normal usage pattern. So we are not putting any like burn-in or HPL load or synthetic load. This is like normal use of the system. And then we monitor this availability on node and system level. So basically availability of the nodes, and then we have some threshold that if we have less than the threshold of nodes, then we consider that the whole system is unavailable. And after this, it's system acceptance and general availability. So are we missing something here? Yes, we are. So then there is the task of integration and localization. So basically, in order to have a good pilot and good availability test, you should already have your system integrated to all site services, user portals, job accounting, support portals, online documentation available. And also, if the pilot is successful, and typically it has been successful for us, it's extremely difficult then to say that okay, nice, pilot is over, so we are now gonna close the shop for, let's say, 2 months and make it better. So at the point when pilot ends, customers, stakeholders, they really want it online. And I think for this integration work, like real physical test and development system, TDS, that's like essential for like any tier 0, but I think also like tier 1 systems. And this TDS, it's also a critical component. So just like if you break your TDS, it's a small scale disaster, and it will delay everything in production. Because you cannot put anything, deploy anything without testing it. But it's still better to have a TDS to make the big mistakes. Then there's the sysadmin training. It's a huge investment to get like half of your or 70% of your sysadmins and network admins for 1 to 2 week classroom training, not responding emails, not responding tickets. This is something that you really have to plan. And I think this TDS system is also essential with training and preparation period. Because like having hands-on with dedicated system, your own system, it's completely different than like looking at slides. And I think for these tier 0 systems, there should be always a phase 0 delivery as soon as possible after the ink has dried from contract to get hands-on on something. Last thing, it's the system security. So when you even think about opening the system, even for a pilot, you need like lots of security contracts, data protection. You have to consider GDPR, physical security on site. You have to have everything planned, documented, in place. And when you have novel bleeding edge technology, there's like lots of these unknowns, 0-day vulnerabilities, and for these landmark systems, the risk for being targeted for attack, it's very high. And if you have a system which is for open science, for thousands of users, open in internet, it's even increasing the risk. And then if we compare to kind of like a legacy HPC systems maybe 10 years ago, where you have a login node, but now we have this modern approach. We have cloud-like services, we have a different kind of desktop GUIs, we have a RESTful APIs. So this attack vector is growing all the time. And also the system stack is getting more and more complicated. Typically like tens of open source technologies. You have Kubernetes, Puppet, Ansible, web services. On a quiet day in Lumi, there's 1 billion lines of log data. So it's also like a really challenge to monitor. So I think this is again like when you are accepting the system or starting the pilot, it's really a leap of faith. Even if your system survived reboot and it's performing well, it's functional, are you really ready to put it online? That's my last bullet. Thank you. Any questions or comments?
Yeah, any questions? I've got a couple, but
I have one and I didn't type it out. But this is Natalie. Thank you very much. That was extremely informative, and it was the kind of information we haven't actually covered in the EEHPC working group, but fascinating all the same. And it definitely impacts availability, it impacts utilization. There's a lot of factors. So it's a real efficiency consideration. But I didn't I don't think I heard you talk about dynamic power swings. And I wonder if you had any testing on dynamic power swings and whether that was the consideration at all. Oh, and by the way, when I mean dynamic, I'm actually talking about, like, let's just say sub 1 minute megawatt power swings.
I think our power swings when we run HPL, they are basically like 2 seconds and 7 megawatts. Esa, do you have any comments on here?
Yeah, I have a couple of comments. I have some information about power swings on size of power swings in the Lumi during the HPL runs, and actually during the GPU HPL there was a stall moment when all the GPUs started to idle, and those power swings occurred during the HPL runs. So I have some data in the lessons next session about the power swings of the Lumi, and I have a power graph from the latest HPL run. But yeah, we were actually the power swings. Our power supply chain survived those power swings. There was no any issue in the power feeds to handle those big swings up and down during the benchmarking. So that was actually tested.
There's a comment from Aaron. I think personally, I think that it's very important that the actual users or sites hosting these systems and administrating systems, we should really have like close dialogue with vendors about the complexity of the technology and the evolution of and landscape of future HPC system software stack. I think currently like there have been like some approaches which have not been so successful, and this should be avoided. So I think the actual users and customers should be involved with the planning more.
yeah, I would concur. I mean, we found layers and layers of software stack that we're like, oh, gotta learn about that too.
It's like that if you see a slide set and there's a 50 nice logos of open source technologies, you are basically in trouble.
Yeah, concur. And then potentially last question. Any examples of challenges in benchmarking and kind of surprises that were either good or bad? I know we had some codes that specifically wanted to see Intel MPI, and we had to do some work on some of those to get to the benchmarks where we wanted them to be.
I don't know. I think for each system, you should always have kind of like this lessons learned about the benchmarks, because it's only after you get the system, you find out that okay, these benchmarks were like useful, and some benchmarks, they might be like completely useless. Maybe the case is not right. Maybe it's not really like fit for the system, even when system is fit for the workload. Pekka, do you have any comments on this?
Yeah, I agree. So we tried to make a very compact benchmark suite, so to extract the minimum viable amount of information, and like Samuli said, some of the benchmark did not behave, especially when procuring a very big GPU system without having an access to a very big GPU system while prepping them. So some of the benchmarks turned out to be, there was something that happens on a scale, and it didn't like a benchmark at the end of the day what we wanted to know. So yeah, that's kind of a, so if one can test the benchmark somewhere before issuing it, it's of course a different thing, but so yeah. So application benchmarks are always bear a risk of ending up benchmarking the benchmarking team and not the solution, meaning the vendor's benchmarking team.
Right. So
There's a
Michael,
question about how far in the future do you queue incoming computational jobs? I don't know if this is related to the fact that we have, for example, currently about 8 days of like full workload on Lumi C, but
So depending on a job size, so if you submit that job today on Lumi G side, it likely goes into execution within the next 24 hours. And if it's small, it's considerably less. On Lumi C, it seems to be quite packed, so one may need to wait for 2 days before it goes into execution. That's of course not desired situation, and I hope the queues will melt. Aaron, do you want to take the other benchmark question now, or on the Q&A?
I don't know where Aaron went, but why don't we go ahead and start the next presentation?
oh, sorry, I was muted. So
we decided to go forward with this as talks.
yeah, why don't we move on, and we'll pick that benchmark question up, because I think that's an interesting one in the Q&A. So Asa, I think you're back up with lessons learned.
Yep. Just a second, I will share my screen. Is it visible?
Yep, looks good.
Okay. So this last session is for lessons learned in the installation and operation. This is more focused on the construction phase because Samuli went through the Lumi hardware installation pretty well in last session. So this is more concentration on the construction phase itself. So as you have seen this timeline before, we had a pretty strict schedule for the building this data center. So actual construction work started in beginning of 2020 for physical construction on this old paper machine building, and our construction was completely ready on the data center side, and integrated system test was done also within a year in first quarter of the 2021. So we had a pretty strict schedule and a lot of people involved in the constructional phase of the Lumi data center. So our data center construction started in Q1 in 2020, and these pictures are actually from the inside the building in end of May on 2020. So in the second floor, we only had the concrete beams in place and some steel structures installed. And in the first floor, there was basically nothing in place yet. So we had 10 different contractors working on the site at the same time. So it's very important that you can schedule and have a ability to have all the contractors working in parallel and doing working with their own area at the same time to meet this kind of timeline. And this timeline couldn't be met if we wouldn't reuse this building and build the data center inside the existing building. So building a whole new data center would take much longer. And other fact that was that, as somebody mentioned, that and Pekka, that we have our system procurement ongoing when the data center building was already started. So our cooling and electrical designs was redefined and finalized during the construction phase when the system vendor was selected. So there is a lot of variation between about the power feeds of the different HPC vendor cabinets and how the cooling is implemented, what kind of temperatures, what kind of water flows and other things there is. So basic design was made with some requirements of the site total power and how much cooling we need to provide to the direct liquid cooled cabinets, but there was a lot of design redefining done during the construction phase. And Q1 2021 data center was ready, and we have this all of the control, safety, cooling, and power distribution was tested in these integrated system tests, which I presented more detailed yesterday. And the data center was accepted for the Lumi, and the first phase installation started on the summer 21 with Lumi CPU partition. So it's very important to have a coordination on the construction phases between the contractors. That needs to be planned very carefully to avoid any major delays on any of these construction phases or in any work of any contractors. So we have also COVID ongoing back then. So a lot of video calls and other tools was used to deliver the information from site to the designers because they couldn't visit on site as they should when we are constructing data center like we did. Actually, it was pretty good that we have this complete 3D model in use to fit designs together. And we have simulation tool to adjust the HPC cooling specifications during the construction and adjust the final components and do some pre-tuning for the control system before the actual system tests. So this reduced time for system testing pretty much to have this kind of tools in use, and avoid with this 3D model we avoided lot of issues in the construction site when you are planning a pipelines and cable routers in the very tight space underneath the data center raised floor. And as somebody mentioned, this HPC system installation started without system vendor on-site inspection beforehand, so our vendor never visited on-site before they first came with the Lumi C cabinets into the Kajaani. And other thing was that this system was installed in multiple phases, so this required a lot of arrangement and people involved on the data center after the building construction phase of the data center has been ended. So we have to have the mechanical people on site from subcontractors to connect the pipelines and do the bleeding for the cooling and connect the power cables and do the power testing and that kind of things. So this multiple phases of the installations is not at least easier to handle. So then couple of lessons learned about HPC operations, and this is the latest HPR run in our GPU partition from this fall, which was actually submitted on the top 500 list. So this is 1 second interval measured for the full GPU partition, and as you can see, the maximum power usage during the HPL was a little bit less than 8 megawatts, so it's quite a small in the bottom of the picture, 7.8 megawatts of maximum power during the HPR run. And about the real life power usage, this is previous month of the Lumi's total power. This includes the CPU partition, and the GPU partition is this yellow line. And as you can see, the real workloads in the GPU partition is about 50 to 70% from the HP power usage that we have measured in the HPR runs. These highest spikes here are from the hero runs that we did in the end of November, when the full system is trained and allocated for the single users to allow to run their big projects with the full scale of the GPU partition, so they are able to use the full capacity of our GPU partition for their workloads. And also in there, the high power swings are involved, like in the HPL. So when we are training the system to the idle load, it is a little bit less than a little bit over 2 megawatts in GPU partition, and then power swings up to 6 megawatts. So there is still those 4 megawatt power swings included in the operational period. And as Samuli mentioned, we have this power cap on the GPUs in place. So we have capped maximum power of the GPUs from 560 watts to 500 watts. But as you can see from this graph, that real power usage is still way lower than in the HPL, and this is because how well the users can implement the potential of the how well they code can utilize the power of the GPUs. So in the normal operations, we are way lower than during the HPL. So then something about the HPL runs. So as Samuli mentioned, that running the HPL in the system size of the Lumi, it's not just a single attempt and then get the results out. So when you were pushing back-to-back HPR runs on the GPU partition, for example, if the run fails with some node failure or there's a network error, you need to push the new run and try to get the result out. And what we noticed that when running these back-to-back HPR runs, our transformer temperature started to increase pretty high levels. So 110 degrees was reached in these two transformers, which are feeding the most of the biggest partition of the GPU cabinet. So then we discussed with the vendor that there should be a little bit more cool down between the HPR runs to avoid this kind of issues. These are 3-phase cast resign transformers, and those are static transformers, which means that there is no any moving parts. And these are usually good choice for high service reliability situations. So those are pretty much service free and highly available and high availability transformers. In normal operations now with the Lumi, the temperatures are somewhere like 70 to 80 degrees. But even this, it didn't cause any physical issues or any blackouts into the system. So actually those transformers can go up to the 140 degrees before they will shut down the power. Also something we noticed during the HPR runs that very high harmonic voltage has detected on our power analyzers. So this is something that at some point old Jim Rogers from the Oak Ridge had some presentation. I can't recall, was it on the in this HPC working group or at some other group, but this is something that we are still working with the system vendor to get these harmonic voltages, get rid of those, because it's possible to do. But this is not the case in the normal operation. This is only was case in the HPR runs that we have seen so high harmonics in there. So a couple of things then about operating at chillers. So we had this original idea from our cooling designers to operate the room cooling chillers with 3 operational modes, as we are doing in the HPC cooling. So free cooling outside temperatures below the 14 degrees, and then partial free cooling from 14 to 18 degrees, and mechanical cooling only over the 18 Celsius degrees. In theory, this partial free cooling could save some energy to allow free cooling heat exchangers and dry coolers to do the cooling first, and then the rest of the cooling is only done by the chillers. But in practice, running chillers condensers such a low temperatures, because if we are using the free cooling, the temperatures are too low, which are then going in the inlet side of the condenser of the chillers. So those couldn't be reliably run. So there was some issues with these devices. So then we, as you can see from this graph, that the minimum operational temperature of this chiller condenser is about 26 degrees, and it couldn't be reached in this partial free cooling mode. So we decided that we are only running our chillers as usual, so only free cooling and mechanical cooling modes. Also, it would be better to build 4 smaller cooling modules instead of having a 2 big turbo-core chillers, because the radiated heat from the air-cooled cabinet was lower than expected, and directly with cooled cabinets are radiating very little heat to the air. So over 98% of the heat is radiated to the water. So chillers are now running about 50 to 60 from the maximum capacity. So this was pretty much issue after the first phase installation when all of the compute devices was not yet in place in the data center. So we had some issues because of the low loads on the chillers to operate those. And also this trying to operate with this partial free cooling was pretty much causing also problems. So then about the HPC cooling, we have these dry coolers installed in top of the roof, and we have over 40 meter or more, maybe in total of 50 meters of pipeline from this free cooling heat exchangers to the chillers, and those pipes are running inside the building, so building is heated, so temperatures in these pipelines are approximately 20 degrees. But when we are running in the fully mechanical cooling, we have no any flow in this cooling loop. So it can end up in the coldest days that we have -20 up to the -27 degrees cold glycol waiting outside and 20 Celsius glycol inside the pipeline before the heat exchanger. And if there is a sudden need to turn from mechanical cooling to full free cooling so that we are stopping the heat production, this will cause problems, because the first is 20 Celsius degrees glycol is coming to the heat exchanger, and we have this mixing valve here, so we are trying to keep this 31 degrees for the heat exchangers. Sudden heat load hits to the free cooling heat exchanger, and this pump needs to start ramping up to maintain the 32 degrees on this side. And then we have sudden incoming -27 degrees Celsius of glycol from the rooftop, and we are mixing still some flow into it, and suddenly this drops dramatically. So we need to start to mixing more heat into the coming glycol from the rooftop, and we need to start to lower this pump speed because this outlet goes too low. So this is something that should be think about in the more in the design phase to have some kind of side flow, constant flow, also in this glycol loop to maintain stable temperatures in all parts of the cooling loop. And also the buffer tanks should be also installed on the outlet side of the HPC cooling to balance load variation from the directly cooled cabinet. And this next picture shows the case that we had to suddenly change from the mechanical cooling to complete free cooling. So these are the cooling group modules 2, 3, and 4. Don't ask why we don't have 0, 1. So as you can see, when we suddenly change from the heat production and mechanical cooling to the full free cooling, the outlet from the heat exchangers to the Lumi started to increase, and it went on the worst case up to the 40 degrees. And when this sudden cold glycol came from outside, it started to drop dramatically, and it did this swing for a while before it was balanced. But this black line indicates what was the measured temperature after the buffer tanks, and as you can see, it balanced these swings pretty good. And this is the worst case that I have seen in this cooling. So it was very reasonable to install this buffer tanks in the outlet side, on the inlet side, on the cooling loop for the HPC. So the variation for the Lumi was only ended up to a little bit over 33 degrees, and then it went about 31 degrees, and then it was balanced at 32 degrees with this set point. So in this case, actually, this HPC cooling was forced from mechanical cooling to free cooling because we had a pump issue on the district heating network. So the heat from the heat pumps couldn't be transferred anymore to the district heating network. Then about the waste heat utilization, this heat pump has required a lot of maintenance and adjustment to get efficiency of then about the reasonable level. Well, one reason for that is that this integrated system test, which we did in spring of 21, was made with 2 megawatt heat load with those heat banks, and adjustments was done, but there was a long delay before we had again that high power usage in the Lumi directly with cooled partition. So because this first phase installation was approximately only less than 1 megawatt in total power, so we had running single heat pump with the 50% or less of its power. And when the full system and GPU partition was installed and our heat production again power started to raise over 2 megawatt per heat pump, we had to redo some adjustment. And other issue is that with the partial heat flow, heat pumps are running most of the time with the partial load, so 60 to 85% of the maximum load, and this has negative impact for the COP. There has been also some leaks.
Hey, so I wanted to just let you know we're coming up on about 5 minutes till the hour.
Yep.
So
I have one more slide left. Yep. Okay, so quickly, so we have to done some refill for the refrigerant gas and fixed those leaks to get the system running as designed. And would be reasonable to implement partial free cooling for the area only when there is no demand on the district heating network, so we could utilize the waste heat only for the area, running a single cooling module on the mechanical cooling and other free cooling. And as I saw, the heat pumps are difficult to operate on these large HPC load swings, which applies mostly on the GPU partitions. And the outlet varies a little bit based on the IT load of the HPC system, so it's hard to maintain optimal circumstances for the heat production. A little bit about power and measurement. So setting up the monitoring system size of Lumi, as Samuli said, there's a billion lines of logs and many measuring points. So it has been challenging to get monitoring operational, and lots of work has been done on that part of view. Also, the power measurement on the HPL is only needed once with such a high sample rate and accuracy, so this should be measured from the compute cabinet itself. Then the last slide is about the cooling water chemistry. So this 32 Celsius inlet on primary loop, which we are running on the data center side, and 36 degrees on secondary water loop in the HPC cabinets are ideal circumstances for bacteria growth. So as you can see, this mesophiles bacteria growth is at its highest on these temperatures, so 32 to 36 degrees. So it would be best based on this graph to have a little bit over 40, about 45 degrees to decrease the bacteria growth of these cooling loops. So this is the crossing point of these two types of bacteria. Biocide dosing should be applied direct to the cooling loop instead of filler tanks to get desired effectiveness of the kill the bacteria growth. And this bacteria growth actually lowers the pH level on the cooling loop. So this also increases the bacteria growth. And as you can see from this graph, pH 8 would be pretty much optimal to have in the cooling loop. So this is something that data center operators and HPC vendors should focus really and with the high priority, because this kind of contamination in the cooling loop can eventually block these fine-graded cooling blocks on the plates, and this can cause cooling issues to the components. Okay. We are pretty much running out of time, but
Yeah,
do
we've
we
got
have
a
any?
minute for a few questions if there are.
It'd be easier to alternate biocides when you're dealing with the situation for the tanks.
Yes, actually, there is a couple of different biocides that has been tested because this bacteria get resistant to the biocide if it's used too long, if we are using too long same biocide. So different biocides need to be used to get desired effective for the bacteria killing.
I think we should actually just call it the hour. This has been a fantastic presentation. Just tons of detail. Really appreciate it. Everything will be posted on the website in the next couple of days, and I'll let everybody know who's registered that it's there. So I really appreciate. Great job.
Thank you.
I'd echo the same. A lot of really good information. So appreciate it. And thank you, everybody.
Thank you also on our behalf for your time and listening.
All right. Happy holiday.
Thank you very much.